All right, so what do we mean by constant acceleration? What are we talking about there? Constant acceleration. Exactly what we said a second ago. We mean that the acceleration in the motion does not change. So in other words, we might say that A is equal to 1.5 meters per second squared. And throughout the entire motion, the acceleration never changes, right? So in real life, you know, acceleration's always changing. When you're speeding up and then you're slowing down. You're speeding up, you're slowing. That's a change of, the acceleration's always changing, right? But in these problems, here with constant acceleration, the acceleration variable is set and it never changes throughout the motion. These equations that we're going to use for these problems only can be used when the acceleration doesn't change. So we might have 1.5 meters per second squared, it never changes. Or we might say that we have negative 3 meters per second squared, and it never changes. That means we're slowing down, or you can say we're accelerating in the negative x direction. And so when we say we might be locking these guys in, they will be constant for the entire motion. All right, for the entire motion. Which basically means that the velocity is constantly increasing at a known rate. It never changes the rate at which the velocity is increasing. So to get an intuitive feel for that, we're going to do something that we've done in the past. We're going to give a little quick example because it's going to tie directly into the equations that we're going to be using to solve these problems. Let's say that you're given the following information. Let's say you're told that your initial velocity, that's v naught, v at time 0, is equal to 10 meters per second. And let's say that you're also given that the acceleration is constant, never changes, at 3 meters per second squared. What is going to happen to this velocity at every moment in time that we go down the road? We want to take a look and see what that is. All right, so let's say at t is equal to 0, what do we know? Well, it means at t is equal to 0, the velocity was 10 meters per second. So the velocity is 10 meters per second. So let's go down the future and just take a look at what's going on. We'll look at 1 second, 2 seconds, 3 seconds, 4 seconds, and 5 seconds. And we've done something like this before, and the reason I'm bringing it up again is a good reason, because as you're going to be able to see from this data how the equations of motion with a constant acceleration work. So when you're accelerating at 3 meters per second squared, remember what we learned. We said that means that your velocity is gaining by 3 meters per second. So the velocity is increasing by 3 meters per second every second. So that means when I get to 1 second, I add 3 meters per second to this because that's my acceleration. So I'm now going 13 meters per second. And then I go another second into the future, I add another 3 meters. So now I'm going 16 meters per second. I go another second, I add again 19 meters per second. Now you can see the pattern. And then it's 22 meters per second, and then it's 25 meters per second. Every second in the future, my velocity is increasing at a known rate. What is that rate? 3 meters per second increase every second. The increase of my velocity never changes. My velocity, of course, changes, but the rate at which my velocity increases never changes. That's what it means. So if we were to plot this data, what would it look like? Well, this is a velocity versus time graph. So let's go and do our best. We'll actually try to plot the points here. It's not going to be exact, but it's okay. We don't need exact. What we're trying to do is just get a feel for what this really is telling us. So this is t, some seconds in the future, and this is velocity in meters per second. All we're doing is plotting the data on the board. So we go 1, 2, 3, 4, 5 seconds. So on the x-axis, we have 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. I guess I could have gone a little farther out. We'll call it 1, 2, 3, 4, and 5. For velocity, we end up starting at 10, and we end up around 25. So we need our scale to go up to 25. So let's just do it like this. 5, 10, 15, 20, 25. Let's just go like this. So 5 meters per second, 10, 15, 20, 25. So we're just going to plot the data. All right, so let's see what happens. At 0 seconds, my velocity actually is given to me that my spaceship or whatever is already going 10 meters per second. So I have a dot at 0 seconds, 10 meters per second velocity right there. At 1 second, I'm going 13. So 1 second, I'm going 13. That's about right there. This is not going to be totally exact, but that's pretty close. 2 seconds, I'm going about 16. So here's 15. 16 is just a little bit above that. At 3 seconds, I'm going 19. So let me go try to find, there's 20. So I'm going to go just a hair below that, right? 19. 4 and 22. So 4, I'm going to go, here's 20. I'm a little higher than that at 22, roughly something like this. And then at 5 seconds, it's 25. So I'll go up here. That's all the way up here at 25, the very top. And it looks like this point was a little low, but anyway, you get the point. What does this look like to you? This is a straight line. I'm not going to be able to draw a perfectly straight line through the points, but I hope you can see that it is a straight line. Any variation in the dots being on this line is just because I'm freehanding it. I'm not doing it on a graph paper. The point isn't to be exact. The point is to tell you what? The point is that when the acceleration is constant, your velocity increases at a known steady rate every second. So what it means is that your velocity time graph is a straight line. So for constant acceleration, the velocity versus time graph is a straight line with some slope, right? Now, what do you think the significance of this slope is, of this velocity curve? This is a velocity curve. Remember, we talked about velocity and acceleration. Whenever we have a velocity curve, the slope of the velocity curve, how much it changes as compared to time, is what the acceleration is. And since this is a straight line, the slope of this line is the same all over the place. The slope is the same at every point here. But we know that the slope of this curve must be the acceleration. So let's figure out what the slope is. We're saying that the slope of this curve is equal to the acceleration, because that's what we define acceleration to be. So what is the slope of this curve? It's rise over run. So it means delta v over delta t, right? Which would mean the final velocity minus the initial velocity over the final time minus the initial time. Now I can put any pairs of points on here. I can use these points, final velocity minus initial velocity and all that, or I can do these points, or I can do these points. The reason I don't care is because it's a straight line. So no matter what points I pick, the slope will always be the same. So let's make it easy. Let's just calculate the slope with these 2 points here. So what is the final velocity? Up here, you can see we used 13 was the final velocity. So 13 minus the velocity here is 10, divided by the final time is 1 minus 0. So you're literally taking the subtraction of the velocities, that's delta v, and the subtraction of the time. So on the bottom, it's going to be 1 minus 0. So what do you have? 13 minus 10 is 3 over 1 equals 3. What is the significance of this 3? What we're saying is the slope of this line is 3. But we already said in the problem statement that the acceleration was equal to 3 meters per second squared. So what I've proven to you by a very simple problem is that if I give you a starting velocity and I give you an acceleration, you've learned a ton already, believe it or not, about motion. You've learned that anytime you have constant acceleration, your velocity curve is always going to be a line. The slope of that line, if you calculate it using algebra rise over run, you're going to get the acceleration, because the slope of any velocity curve always is the acceleration, right? That's what we learned before. So why do we do all this stuff? Because we kind of did that in the past. In the previous lessons, we talked a lot about slope and we talked about all that stuff. Why are we doing it again? Aren't we supposed to be learning about the equations of motion? Yes, because here's the deal. Let's go and take this graph. Now we have proven to ourselves that motion with a constant acceleration is a straight line velocity graph. Let's go over here to this board and kind of start over a little bit. We're not going to start over like crazy. We're going to start over a little bit. What I'm going to do here is I'm going to draw, as best I can, another velocity graph. So now we're going to start here. This is the velocity in meters per second. So since we're always talking about constant acceleration problems, you now know that the velocity as a function of time for any graph of constant acceleration, which is what we're doing, is always going to look like a straight line. So let's just draw it like this with some kind of straight line. This is not supposed to be curved here at the end. It's a straight line. All right? Now, we already said that the slope of this curve is the same everywhere, which was 3, which was equal to the acceleration. So you already know then, right? We already know that the acceleration, I'm going to draw the acceleration graph right underneath it here. So this is time, and this is acceleration. What is the unit of acceleration? It's meters per second squared, so we'll use that as the unit here. So what is the slope of the curve here? Well, let's just pretend it was 3, it doesn't matter. What is the slope here? Well, it's the same thing. It's 3, or it's 3 here, 3 here, 3. If the slope of this line is different, it doesn't matter. The slope of it is the same at all points. So the slope of the velocity yields the acceleration curve, but no matter what the steepness of this line is, it's always going to be the same, and that means that your acceleration is always going to look like a constant horizontal line. Which makes total sense because we're saying it's constant acceleration. We're saying the acceleration never changes over time. In this example, we said the acceleration was 3 meters per second squared. It never changed. And what we have shown is that the acceleration never changes. If this were 3, I could put a 3 here, but I don't want to put numbers anywhere. If this were 3, then it would never, never, never change. So I left the top of the board open because I want to draw the position curve. But even before we get to the position, you now know for constant acceleration, the velocity is a straight line with some slope. The slope of that line gives you the value of the acceleration over here, but it never changes because it's constant acceleration. All right? Now, before we go any further, what have we learned from this? We know from algebra that this is telling us that this acceleration is just a number. So if I had to write an equation, because remember, this is all about finding the equations of motion. So what is the equation for the acceleration? Well, all we know is it's equal to a constant. It's usually given to you in your problem, or you can calculate the value of A given everything else, but you know that once you find A, it's always the same for that problem because this is only constant acceleration problems. Now, what does this look like? This looks like a straight line, right? So what is the equation of a straight line? So we expect, let's see, what am I going to write here? We expect that the equation for the velocity as a function of time to be a line. Something like y is equal to mx plus b, right? I'm not going to give you the equation yet, but all I'm telling you is that you know from looking at it like this, you know that the equation for acceleration is going to be a constant. You know the equation for the velocity is going to look like a line because it is a line for every problem of constant acceleration. Now let's go one level up higher and say, well, now we know the velocity is always changing. What would be a graph? I wish I would have drawn that lined up a little better. Sorry about that, but it's pretty good. We'll go here. Now we're going to say, what is t, or the position x, as a function of time? How does the position of x change? In meters. That's the unit there, right? Well, what do you think is going to happen? You have to kind of like use your imagination a little bit here, but if you think about it, what's going on here is in the beginning of the motion, the velocity is lower. But as time goes on, I'm actually moving faster. So here I might be going 10 meters per second, let's say, like look in this problem. Initially I was going 10 meters a second, but several seconds later I'm actually going much, much faster, over twice as fast, 2.5 times as fast, 25 meters per second. So even though this looks like a straight line, of course my position is not going to be a straight line because in the beginning of the motion I'm actually going slow. But then several seconds later down the road I'm going much faster. So whatever this curve looks like, I'm going to be covering a small distance every second in the beginning. But then when I get several seconds later, I'm going to be covering a lot more distance because I'm going so much faster. So I'm going to give you the punchline here. The shape of the curve for position for this type of motion looks like something like this. It's a curve. It's a parabola, basically. It's kind of a kinky looking curve. It's not exactly smooth, but it's a curve. It's a parabola. So for constant acceleration motion, we get a parabola. For the position, that's x, as a function of time. So because it's a parabola, what type of equation do we expect to get for the position? We expect something like x of t is going to, I'm going to put the squiggly equal because it's not exactly equal to this, but it's going to look something like a function of t squared. Because a parabola, if you think back to algebra, y is equal to x squared. Like I did y is equal to mx plus b here. So you expect this to be a function of t squared because t is my variable here. And actually this is a little sloppy. What I really mean to say here is instead of mx plus b, it's going to be some slope times time plus some intercept. Because in algebra we use x and y, but in physics we use time and velocity. So the independent variable is always going to be timed here. So the slope, or the equation of motion for the velocity is going to be some line where time is the independent variable. The equation for this parabola, for this position, is going to be some kind of t² function, because that's what a parabola looks like, you remember from algebra. So now we're at the punchline. Is what I could have done to start this lesson off is I could have just given you all three equations of motion. But now that we've motivated it from a real problem, you now know that the position curve should look like t², because it has to be parabolic. And the velocity curve has to be linear like a line, so it has to have some form that looks like a line. And if you wrote the acceleration down, you know it's just a constant. Those are basically the equations of motion in physics that can be used to solve every problem. So without deriving those equations, we could derive them, but I wanted to do this as more of an explanation more than anything else. Let's go and take a look at this. The first equation of motion, right, that corresponds to position, is going to look like this. X is going to be equal to v naught t plus 1/2 at². Now, we are going to pick this equation apart a lot in the next section. We're going to explain more about what the equation means. All I'm trying to tell you right now is that the equation of motion that governs the position as a function of time looks like a parabola. It's got a t² term. Yes, it has another term here. That's just going to slightly change the shape of the parabola, but it's parabolic for the exact reason that we talked about here. It has to be, because you're going faster later. So here in the later part of the motion, you're going so much farther for every second because you're going faster. In the beginning of the motion, you're not going nearly as far for the same second because your velocity is so much slower. And the equation of motion for position has a t² term in it. Notice that what you have here, you have the distance you've traveled, initial velocity times the time, plus a half. We'll get to why there's a half there later. Acceleration, this is just a constant. This is how fast in meters per second squared you're accelerating, times t². Now the next thing we want to talk about is this guy. The equation of motion that goes along with the velocity. That one is going to look like this. The velocity at some point down the road in time is equal to the initial velocity plus a times t. This is the equation of motion for velocity. What does this look like? It looks like a line. There's a slope in front of the t. Remember, mx plus b, or mt plus b. Whatever's in front of the t is what we call the slope. Looky here. Well, look what's in front of the t. A. That's the slope. Remember, we just said the slope of this thing is equal to the acceleration, and that's why the acceleration is in front of the t, because it is the slope of that line. This is the y-intercept. So if I wanted to flip it around, it would be at plus v naught. So mx plus b, essentially. The y-intercept being the initial velocity. In fact, look at our curve. When we started off on our original graph, we started off with an initial velocity of 10 meters per second at time 0, so our line actually intersected the y-axis right here at 10. This is the y-intercept, so we're saying the y-intercept is 10. That's the starting value of the velocity, which makes total sense because v naught is the starting value of the velocity. So what it means is, if you put time 0 in here, this term drops away, and that means your velocity is equal to your initial velocity at time 0. But as time goes on, you start adding in this increase in speed due to the acceleration, and so you're adding it to your initial velocity. And so your final velocity down the road is your initial velocity plus the increase of speed that you've gained because of your acceleration, right? So these are the two most important equations of motion. And we can derive them using other methods. There are other ways to do it. But a graphical way of explaining to you what it intuitively means, I think, is actually worth more than a formal derivation, because you understand why this one has a t² and why this one doesn't, right? Now, there's one more very important equation of motion that you're going to use a lot. Notice that there is a time in this equation. It's actually in two places. And there's time in this equation. If I were to solve this equation for time, I'm not going to do the algebra because I don't think it's actually worth doing. But if you solve this equation for t, and then stick it into here and into here for the value of, because remember the time here is the same as the time here, so I can solve this equation for time, stick it in here, and then I have another equation that will no longer have time because I'll substitute in here, and then rearrange and solve, then I can actually arrive at another very useful equation of motion, and that is the following. V² is equal to v naught, initial velocity, squared, plus 2 times a times x. And this is what we typically say is the third equation of motion. It actually, notice, doesn't really come from anywhere new. It basically is just taking the first two and eliminating the time variable. How do we do it? We solve for time, plug it in, and then we rearrange everything, and what you're going to get is this equation. Notice that if we stick this thing in here, we have squared terms. That's why everything starts to get squared, and that's why this variable has some squared velocities in it, because when we solve for t and stick it in here, we're going to end up squaring everything. But that's all you end up doing. I'm not going to go through it. Isn't really terribly relevant. All we're going to end up doing is using these three equations to solve problems. But why do we have three? What this basically tells us is we use this equation when we want to know the final position of the ball or whatever we're throwing. We know how fast it started off. We know its acceleration. And we know how long it traveled. Then we can find out how far away it is from its initial starting point. We use this equation when we know how fast it started, we know its acceleration, we know how long it travels for, and that tells us the final velocity that it's at after it's finished accelerating. This equation, notice, doesn't have any time in it. So we actually can figure out the final velocity here by only knowing how far it traveled and its acceleration and its initial velocity. So we use the third one in cases where the problem doesn't actually tell you how long the ball's flying for. Because when you think, or not, I say flying, but what I mean is down the x direction. Because when you think about it, if we know how far it went, and we know the acceleration, and we know its starting velocity, that should be enough information for us to figure out its final velocity, because we just found it by substituting in there. But at the end of the day, these three equations are the fundamental equations of motion in physics. What we're going to do is we're going to pick these apart in the next section and explain a little bit more intuitively why they work the way that they do, just as a general background. But ultimately, what you're going to have to do when you're solving your problems is you're going to have to pick which equation to use, and actually many times you'll have to use more than one of the equations. And which one you use just depends on what the problem is that you have. Sometimes you're given time. You know how long the baseball was flying for, so you're probably going to use one of these equations. Sometimes you have no idea how long it was, but they might tell you how far in distance the train was going down the tracks or something. Then you might use this one because you don't need the time for this equation. And also, these equations are set up to solve for these variables, but many times you might have to find A, for instance. So you might have to plug everything in and find A, so you'll have to use algebra to solve for A once you stick everything back in. But what we're going to do is we're going to use these equations of motion to solve lots of problems. First, moving down a straight line, right? And then also they're also applicable when you drop things from the ceiling. Why? Because in gravity field, everything accelerates down at the same rate, the same gravitational acceleration. So we're going to put that gravity acceleration in for A, and we can solve problems with dropping balls and dropping things from a tower and stuff like that. So we're going to do and use these equations for that. They're very powerful. And then later on, when we get into two-dimensional motion, you'll see that these equations are also used in there as well. So these are central and fundamental. So follow me on to the next lesson where we're going to talk a little bit more about these equations of motion. We're going to give you a little more intuitive feel for what they really mean, and then we're going to solve a lot of problems to give you lots of practical practice. Learn anything at mathandscience.com.